Hi, in this lecture we will talk about the material balance reactions. So for a start, let's have a brief review of the thermodynamical terms that we will be using. So we have a system, which is defined as any matter identified for investigation. It's your topic of interest. And then you have your surroundings, which is the remainder of the universe. So basically, your universe consists of your system, which you have of interest, and the surroundings, which consists of the rest of the universe. Then we have boundary, which separates a system from the surroundings. So the boundary can be real, such as the walls of, say, a bioreactor, or it can be virtual and nominal. For example, you have a boundary line where there is a great change, or in a certain heterogeneous system, you have the rest of the bulk concentration, and then you have an area. There is no boundary line there, but that is an area where the concentration, for example, of a solute starts to deplete. So that's an example of a virtual boundary. So in here you can see, so you have if the box is your universe, the system is the contents of your flask, and the boundary there, which is the real and tangible boundary, can be the walls of your flask, and then the surroundings is the rest of the interior of the box. So we have several types of systems. So we have the open, closed, and isolated systems. So for the open system, there is an exchange of energy and matter happening. So the total amount of energy is not constant inside the system. So example, you have your solution in an open flask. So you have an exchange of energy there. So the solution inside, for example, if it's a cold glass of water, you left a cold glass of water on the tabletop. So you have the energy, the heat energy from the surroundings can enter, and then later on you will see that the temperature of the water will rise, and will until it reaches an equilibrium with the rest of the surroundings. And then it's also open. So as you can see, some of the water can evaporate out of the glass. Now, if you have a closed system, there is an exchange of energy, but there is no exchange of matter. So the amount of matter is constant, but the energy is not. So you have for example, the same example, you have a glass, but you cover it, say it's a bottle of water, a covered bottle of water. So there's no evaporation happening, so the amount of liquid inside is the same. However, for example, if it's an icy or cold glass of water with a cover, later on it will reach an equilibrium with the temperature of the room. So you have an exchange of energy from the surroundings to the system, and vice versa. And then you have isolated system. In an isolated system, neither energy nor matter can pass through the walls. So there's no exchange of energy or matter. So the amount of energy, since there's no exchange, the amount of energy inside the system is constant. So that's an example of that if you have your thermoflask. So I think there are current models of vacuum flask right now where you can keep your beverages cold for a very, very long time. So it prevents, although not 100%, it prevents the exchange of energy. So the temperature, as much as possible, will remain the same inside the flask. So those are different types of system. So for a process, so the process is anything that causes change in the system and or its surroundings. So we have several types. You have the batch process, which operates in a closed system. So there is no input of there's no exchange of matter as long as the process is taking place. An example of that, if you are fermenting wine, so you do a batch fermentation. So at the start of the fermentation, you close the bottle and then allow it to ferment. So you do not open the cask until the process ends. So that's an example of a batch process. And then you have a semi-batch. It can allow either input or the output of mass. And then for the fed batch, you input material during that time of fermentation. So for example, you start the fermentation last week. So it's supposed to end next week, but you open it and you added more sugar, for example. So this is a fed batch. And then you have a continuous process. The continuous process allows matter to flow in and out of the system continuously. So there's a constant flow movement in the process. So aside from that, we also need to define about equilibrium and steady state. So the steady state describes the process in which the properties of the system, such as temperature, pressure, and volume, doesn't vary with time. Whereas we have an equilibrium. Actually, some people tend to mix this up. They are not exactly synonymous, or they are not strictly the same terms. So an equilibrium describes a system in which all opposing forces are counterbalanced, meaning there is no significant changes in the properties of the system. So, for example, in an equilibrium in a system in equilibrium, you have the rate of the forward reaction is the same as the rate of the backward reaction, but that doesn't mean that the elements of the system is not moving at all. So it's actually moving. So a system in equilibrium is considered a system in a steady state because since there is no significant changes in properties, you cannot observe significant changes in temperature, pressure, volume, etc. However, you cannot say that a system in steady state is strictly a system in equilibrium. So it's not always like that. Now, a steady state more on refers to the observable parameters. So there's no change in the observable parameter in a system, although that doesn't mean that your system is already in equilibrium. So that is one of the difference between steady state and equilibrium. So one of the main tenets in bioprocess engineering, we have the law of conservation of mass. It's actually very important consideration here. So in the law of conservation of mass, you cannot create nor destroy matter and energy. So you have any amount of mass or matter going in the system must be equal to the amount of matter going out the system. So given a component A, what if mass in is not equal to mass out? So if you have what if it doesn't, it's not equal? So first, you need to check something must be wrong with my experiment. So the system must have a leak. Or if you are just looking at a certain specific component, for example, glucose, the component can be consumed or generated in a reaction. For example, the glucose is consumed by the bacteria in the system. So at the end, it's no longer, it disappears during the process. Or there are accumulation. Usually, if you look at it in continuous processes, so there are accumulations in the system. So the volume of the system or the amount of matter in the system is not constant. So this is the general mass balance for a component of a system. So you get the amount of component A coming in minus the amount of component A coming out of the system, and then add it with the amount. If A is generated within the system or during the process of the system, you add it up and then minus the amount consumed. It's equal to the amount accumulated. Now in a steady state system, that mass accumulated is zero. Because remember, steady state is a state whereas your parameters are constant, and one of those parameters are the volume or the mass inside the system. So for a steady state system, the accumulation is zero. So here, let's have an example problem. We have a continuous process. So there's a continuous inflow and outflow of material. So it's a continuous process set up for treatment of wastewater. So each day you have 10 kilogram of cellulose and 10 to the 5th kilogram. So that's 10,000, tama? Or no, 100,000 kilogram of cellulose and 1,000 kilogram of bacteria entering the feed stream. So while you have around 10 to the 4th or 10,000 kilogram of cellulose and 1.5 times 10 to the 4th kilogram of bacteria living in the effluent. So if the rate of cellulose digestion by the bacteria is 7 times 10 to the 4th kilogram per day, the rate of bacterial growth is 2 times 10 to the 4th kilogram per day. The rate of bacterial lysis is 5 times 10 to the 2nd power kilogram per day. What are the balances for the cellulose and bacteria in the system? So the first step is always analyze what you have. So our base is 1 day because most of the units is given as a day. So this is kilogram per day. You have kilogram per day, or input per day. So for every each day, so you have an each day there. So the easiest one is to get a basis of 1 day. Although it's up to you, you can write it as per hour if you want it per hour, or even per second. You just need to convert these units into a per hour basis or per second basis if you want. Now, since you have a 1 day, so let's start with cellulose. So you do not mix up cellulose and the bacteria. So cellulose is for cellulose, bacteria is for bacteria. So that is one important thing to look out for. Now, you have coming in 10 to the 5th kilogram, coming out you have 10 to the 4th kilogram. The amount is consumed, that the keyword here is digestion. So you have cellulose digestion, 7 times 10 to the 4th. And then there is no generation of new cellulose inside. So just plug it in minus mass out, plus generated, which is 0, minus mass consumed, is equal to the accumulation. And our accumulation is 2 times 10 to the 4th kilogram. So for the biomass, again, we define our basis, which is 1 day. And then, what are the amounts? So coming in, 10 to the 3rd kilogram, going out, 1.5 times 10 to the 4th kilogram, the amount consumed. So how do you know it's consumed? Basically, it disappears. What is the bacteria or the component is disappearing throughout the process. And the way the bacterial is being consumed or disappearing is basically the lysis of that bacteria. So you have consumption, which is the lysis, 5 times 10 to the 2, and then you have generation, bacterial growth. So they are growing, dividing. So you have your cell division going on there. So you have the rate of growth. So plug it in your equation, you get the accumulation. So the system is not in a steady state. So there's a rate of accumulation of 5.5 times 10 to the 3rd kilogram of bacteria per day. So anyway, that is a simple application of the mass balance. So just input all the needed values you have. So we have several types of material balances, or mass or material balances. So we have differential balance. It's just like what we did a while ago. So that is used for continuous processes. So the basis is on flow rates. That's why our basis is a time. So we have per day, per hour, per second. And then we have integral balance. Integral balance are used usually for batch, semi-batch, and fed batch processes. So we are basing it on a quantity or mass over a specified period of time. For example, if you have in the batch process, you have usually it's the substrate. The basis is the substrate. You have 1 kilogram of the substrate coming in for that batch. So you have in a single batch, for example, the recipe for a single batch of, say, fermentation is 1 gallon of fruit juice. So the basis is for every 1 gallon of fruit juice, how many bacteria do we input, how much alcohol was observed, something like that. So these are some things to consider when doing general mass balance reaction. So we need to define if there is a reaction or no reaction in our system. So the total mass of a system with reaction is equal coming in. So mass in is equal to mass out. This is in a steady state system. So a steady state system, you have no accumulation. So you have the total mass coming in is equal to the total mass going out because zero accumulation, steady state. However, if you look at the moles is we are looking at individual identities of the components of the system. If there is a reaction, do not expect that mass in is equal to mass out. It only happens if there is no reaction. The same goes for the type of a certain molecular species. For example, glucose in a fermentation, that's a process with reaction. So do not expect that the amount of glucose in at the start will be the same as the amount of glucose at the end. So it's not. So if there is no reaction, you just observe that there should be. So another one is mass and moles of molecular species. But in terms of atoms, if you are going to count the carbons, the total amount of carbon going in, as in carbon atoms only, So you should expect that even with reaction, you will get the same amount of carbon atoms coming out. The same goes for the moles of your atom itself. So remember, even if you do reactions in a certain chemical reaction, the amount of atoms at the start and at the end of the reaction is still the same. We are still applying the law of conservation of mass. So you should take a brief review of your stoichiometry on that. So you have that amount. So all in all, you have mass in plus mass generated is equal to mass out plus the mass consumed. So we have several procedures for material balance calculation. So unfortunately, I think it didn't translate well. So I'll just, here is the better process of your diagram. So we need to draw a clear process flow diagram, select a set of units, and we need to state it clearly. So this is in the part of the analysis step. So first, you need to know a clear visualization of your system. Are there anything going in? And then is there only a single feed flow coming in? Is there a single outflow going out? And then you need to select a certain set of units, because you cannot add, multiply, or divide, or rather add and subtract, or even compute of different units. So you should be very careful of that. So I'm always stressing that you're always write the units during your calculations, even during your solutions. Always write the units. And then state all assumptions applied to the problem and identify which components of the system are involved in the reaction. So let's have this example. The fermentation slurry containing Streptomyces canamyceticus cells is filtered using a continuous rotary vacuum filter. So the slurry is fed to the filter at a rate of 120 kg per hour, and 1 kg of slurry containing 60 grams cell solids. So to improve filtration rate, particles of diatomaceous earth filter aid are added at a rate of 10 kg per hour. The concentration of kanamycin in the slurry is 0.05% by weight. The liquid filtrate is collected at a rate of 112 kg per hour, and the concentration of the kanamycin in the filtrate is 0.045%, weight by weight basis. So that's by weight again. Filter cake containing cells and filter aid is removed continuously from the filter cloth. Now, what percentage of water is in the filter cake? And if the concentration of kanamycin dissolved in the liquid within the filter cake is the same as that of the filtrate, how much kanamycin is absorbed per kilogram of filter aid? So first, we need to draw the process flow diagram. So we have your system, the filtration setup. So this is the system. So coming in of the system, you have the fermentation slurry. What are the components of your fermentation slurry? So the total amount of the fermentation slurry is 120 kg per hour. So it contains 6% cells and 0.05% kanamycin. Also coming in, another feed stream, you have the filter aid. That it comes in at 10 kg per hour. And then, what goes out? You have the filter cake and of course the filtrate. So the filtrate is stated at 112 kg per hour going out, and you have a 0.045% kanamycin in the filtrate. So we have now a visual of the system. So the enumeration, the list of these values now has a more detailed, or we can now better visualize what those values meant. So we have the process flow diagram. And then we need to state our assumptions. So let's assume that this is a steady state system. So what is the basis of that? So we have filter aid is continuously removed. So we can assume that there should be no accumulation, because in the filtration setup, of course, you accumulate the solid particles in the filter. So it's continuously removed. So let's assume that there is no accumulation. So you have a steady state system. And then the filtrates has no solid. So the filtrate is, of course, filtration. So we assume that this is purely a homogeneously liquid solution. And then absorption and release of kanamycin by the cells during the filtration is negligible. So we can assume that the amount of kanamycin coming in is the same as the amount going out in the filtrate and as well as in the filter cake. So filter aid entering the system is dry, so that we can say that all of the water from the system comes from the fermentation slurry and not from the filter aid. And then all liquids except kanamycin is considered water. So of course we all know that in the fermentation slurry, that's not strictly water. There are many different things dissolved in that. For example, the remainder of the culture broth, the waste materials, etc., etc. But to simplify everything, because we are not really obligated to get a concentration of that nor identify them, let's just assume all of them are water. So let's write them. So we have your the next step. So remember, so we have we have our assumptions. We drew the process flow diagram. So we also have the set of units stated clearly. So we can also, based on the units, we can have your basis. So we can have a basis here of, since this is usual per hour for a continuous system, so let's just say the basis is 1 hour. So most of our units are in kilograms, and then this is concentration value. So let's just put kilograms as our unit. So let's write your balance table. So from what we know in the given, so we have the fermentation slurry, the total is 120 kilograms. This is 1 hour. Our basis is 1 hour. So the units included there, we will be doing the units as a single. Let's just be uniform with the units. So let's all of them expressed in kilograms. So the total is 120 for the fermentation slurry. And then the filter aid, since the filter aid is dry, so there's no water in there, so it's just the filter aid, the diatomaceous earth. So the total coming in is 10. So only the component of this string is just the filter aid. So the rest are 0. So this is 10. And then for the cells, we say it's 6%. 6% of the slurry is cell, so get 6% of 120, you get 7.2 kilograms. The same goes for kanamycin. So get 0.05% of kanamycin, you get 0.06 kilograms. So the filter aid is, there's no filter aid in the fermentation slurry, so 0. And then we do not know the water yet. So water, although the rest must be water, but it's not explicitly stated, so we still haven't calculated yet what the amount of water here. So that's for the feed stream. Now going to the outflow. So going out, there's of course it's no fermentation slurry, no filter aid. So what is coming out, is your filtrate and the filter cake. So for the filtrate, you have a total of 112 kilograms. There is water, of course, in there, but we still do not know. There is no filter aid, so this is purely homogeneous mixture. So no filter aid, and of course there is no cell, because again the assumption is that there is no solids in your filtrate. So cells are considered solids, so there should be no cells here, nor there should be filter aid. So what is in the slurry is only the kanamycin and water. So the amount of kanamycin is 0.045% by weight. So 0.045% of 112 is 0.05 kilograms. So this is our table. So as you can see, you have values there, question marks. These are things we still do not know yet and what we should look for. So again, I'm writing this balance here up so that it's easy to see what we are working with. So let's go with balancing the water. So how much water are coming in the system? So the only source of water in the system coming in is from the fermentation slurry, and we do not know that. So how do we calculate that? So if the total is 120 and we only have the cells and the kanamycin, so 120 minus 7.2 minus 0.6, you get 112.74 kilogram. That's the amount of water coming in. So water in, since there is no reaction in the system, we can say that the amount of water in is equal to water out. So what is the amount of water going out? So we have water in the filtrate, because water can come from the filtrate and the filter cake. The filter cake also contains water. Just to clarify, the amount of water going in comes from the fermentation slurry only, but the amount of water going out, there is water in the filtrate, of course, and there's also water in the filter cake. So we do not know how the water is partitioned. So we get here what is the amount of water in the filtrate. So in the filtrate, just like how we do the fermentation slurry water, so we know the total, and of course the only component of that is kanamycin, so the rest are water. So it's a simple elimination. You get 111.95 kilograms. So that's the amount of water in the filtrate. So water in is equal to water out. So you have coming in from the slurry, you have 112.74, and then going out, it's your water in the filtrate plus the water in the filter cake. So a simple subtraction, you will get 0.79 kilograms of water in the filter cake. And then the next one, we have kanamycin. So we can solve now for kanamycin. So kanamycin, all of the source of kanamycin is from the fermentation slurry. So you have 0.06 kilograms. And then going out, you have kanamycin in the filtrate, that's 0.05 kilograms. And then you also have kanamycin in the filter cake. So what's the amount of that? So of course, it's just a simple balance. So what's the remainder? From 0.05, you had 0.01 kilogram. And then for the filter cake, let's look at the filter cake now. So the filter cake, you have your 7.2 kilogram of your cells. So what are the components of your filter cake? Your filter cake contains the cells. So the cells, all of them comes out of the filter cake. And then you have an amount of kanamycin going out as well. And then the filter aid, since this is 0, so all of the filter aid coming in must go out through the filter cake, and then a bit of water. So just a simple addition. So you have 7.2 of the cells, 0.01 kilograms of kanamycin in the filter cake, plus 10 kilogram, that's your filter aid going in, and then the filter aid going out. And then 0.79 kilogram, this is for the water. So the total amount of the filter cake is 18 kilograms. So if you plug in everything that we already know, so we get this completed table. So 7.2, so that the cells only goes out through the filter cake. The kanamycin, so most of them is goes out through the filtrate, and then but some are in the filter cake. And then you have the filter aid only going out through the filter cake, and then water, distribution of water from the filtrate and the filter cake. So that is your amount. So just get a total of everything. So this is one way to check if you are you do this correctly. So this only happens if there is no reaction. So if there is a reaction, do not expect equality here on everything. So you have a total 130, water 112, filter aid going in, coming out, and then going out and coming in, you have 10 is to 10, 0.06, 0.07. So everything is equal. So the question here is, what is the percentage of water in the filter cake? So just get water, filter cake, 0.79, divide 18 kilogram times 100%, you get 4.39%. So if the concentration of kanamycin dissolved in the liquid within the filter cake is the same as the filtrate, how much kanamycin is absorbed? So the amount of kanamycin absorbed in the liquid is 0.05%, 0.045%. So 0.045% of your of the liquid part of your filter cake. So the filter cake also contains water, remember. So if you add that with the amount of kanamycin, because kanamycin is considered liquid, it's dissolved in the liquid portion. So you add it. So what is 0.045% of that? So you will expect that the amount of kanamycin in the liquid, dissolved in the liquid, is 3.6 times 10 to the 4th. However, from our balance, the kanamycin should be 0.01. So that means there is a loss there's a missing amount of kanamycin, and that kanamycin can be absorbed by the filter aid. So the amount absorbed by the filter aid is the missing portion from the 0.01, so it's 9.64 times 10 to the negative 3 kilograms. So just get the percentage. You get 9.64 times 10 to the 4th kilogram per kilogram of kanamycin. So that is how you do a simple mass balance without reaction. Now, this is for your activity or assignment. So do this, just follow how we do. So I think it's a good idea to use table. Although if you do not want to use this type of table, it's up to you. But what is important is you are actually able to answer this one. So I'll just be giving you freedom to do your solution on your own, on how you understand the problem. But just remember the basic steps. So you need to, in your analysis, especially this in the analysis, you need to create a clear process flow diagram and then define your system. So this is a reaction. This is a process with reaction. So that is for your assignment. We will discuss this, your answer on this one. So I expect that by the time that we do the video conference, you already have an answer for this one. So, or at least you started doing this one. If you weren't able to arrive at any answer, at least you have something, you have started something. Okay? So you have that. Now, before we conclude this lecture, so we will just be adding some terms you will usually see when you look at biological process or bioprocess systems. You have recycle, purge, and bypass. So in your reactor, for example, in a bioprocess, you have a reactor. So here is the feed stream going in. So what does a recycle mean? So sometimes the feed stream, so going in and then coming out. And then you want to, usually the recycle, it contains the cells. So for example, in a fermentation reaction, of course, the cells can also be used again during the reaction. So you want to reuse the cells. So you will get those component and then you return it back to the feed stream. So that is what we mean by recycle. Whereas in the purge, so the purge is the one that we are going to eliminate definitely from this. So basically, we use the term purge to define waste stream. So these are the material that is eliminated as waste from the system. So this is not a purge stream, although it also goes out of the reactor, it doesn't enter anymore. But usually this is connected to the next process and is part of the product. But the purge is usually the waste that is eliminated from the system. So the next one is bypass. So bypass is if you have your feed, the total feed, the portion that doesn't go through your process. So for example, a filtration. It doesn't necessarily always mean a fermentation. So it can be a filtration, it can be centrifugation, or any type of bioprocess. The bypass is that a portion of your feed that doesn't passes through your process. You do not apply the process in that certain percentage of your feed. So that's the bypass. So it bypassed your process. So you remove that and then it re-enters from the outflow of the process. So that's basically the bypass. So that's it for now for the material balances. So please do the assignment and we will be discussing that in your video conference.